Good afternoon, students. Today's topic is physiology of hearing. Hearing is another important special sense which is a gift from God without which we can't imagine our life. So this hearing we will discuss under three separate classes. So today is the first part of hearing. So every special sense is important in its own way. So in today's class, how important hearing is for our life. So hearing is important for two purposes mainly. One is communication and for localization of seen or unseen sound sources. So in our day-to-day life, from the childhood for the development of language or for the child to speak, hearing is very essential. So if a newborn child is deaf from the birth, automatically he will become dumb. So why? Because without hearing, he will not be able to understand anything. So that's why it is a very important, crucial, special sense for our life, and also for determination of location of unseen or seen sound source. So if the person is not able to see, without seeing also, the person is able to locate sound sources with this special sense of hearing. And the scientific study of sound waves is known as acoustics. So before proceeding to physiology of hearing, so it is important to know some principles of acoustics or the physics of sound waves. So you all have this physics of sound in your intermediate. So just a brief review of some of the important principles of acoustics. So what is required for normal hearing, or the uh, steps included in the normal physiology of hearing? The first one is adequate stimulus. So this is the property of receptors. So for any receptor to respond, it should have adequate stimulus. So the adequate stimulus for hearing is sound. And then the next step is conduction of the stimulus or this sound to sensory organ of hearing. So what is the sensory organ of hearing? Nothing but organ of Corti, which is located in inner ear. And then sensory transduction of stimulus at organ of hearing. So in the organ of Corti, there will be some processing of hearing which will be taking place, and neural transmission of signal. So from the organ of Corti, so there will be auditory pathway. So that will be the neural transmission of the signal, sound signal. And then central auditory processing of this sound stimulus at brain. So central means in the central nervous system. The auditory pathway, it will be finally entering into the auditory cortex. Some important points about sound. It is a form of energy that propagates in the form of waves of compression and rarefaction, which are produced by vibrating objects. So vibrating objects like a vocal cord and tympanic membrane in our ear. The speed of sound depends on the medium through which the wave passes, that is air or water. And in air, the speed of sound is 343 meters per second, and in water it is 1482 meters per second. The sound frequencies audible to humans range from about 20 to 20,000 cycles per second. And the sound intensity is expressed by taking logarithmic ratio of two sound intensities, the numerator being the sound intensity of interest, and denominator being a reference sound intensity, and then multiplying by 10. So decibel is taken. So it is the unit for intensity of sound. So decibel is calculated by 10 log J, that is intensity of sound of interest or intensity of the sound heard, by JR, that is the intensity of reference sound. So if we calculate with using this formula, we will get the decibel value. So the normal decibels for hearing will be 0 decibels, that is reference or standard sound, and 10 decibels like paper being gently folded, that sound, and 10 to 30 decibels is whispering sound, and that 40 to 60 decibels will be normal conversation sound, and 60 to 80 decibels is heavy traffic noise, and 80 to 100 decibels is loud motor horn, and 120 to 140 decibels is painful and damaging to the organ of Corti. So the properties of sound the ear detects are of three dimensions. One is intensity, and other is frequency, and one more is complexity. So intensity or the amplitude of the sound waves determines the loudness. Okay. So if we see here, the higher the amplitude or the intensity, the higher is the loudness of the sound. And then the frequency, that is the number of waves. Okay. So the lower the number of waves or frequency, lower will be the pitch. Higher the frequency of sound waves will be having higher pitch. And complexity is the wave pattern. So it is a simple wave pattern. Here there is complex wave pattern. So that determines the timbre or quality of the sound waves. So this is important for musical sounds. So these are very complicated waveform but have repeating pattern. So this complex waves have repeating pattern. So that will be determining the timbre or quality of sound waves. So this is particularly present in musical sound waves. So the pressure level, decibels, and then frequency and complexity of sound waves are the important three properties of sound. So if you see the wave patterns of sound, A is the normal recording of a pure tone, and B is the greater amplitude than A, and C is having same amplitude as A but higher frequency, and so its pitch will be higher. And D is a complex waveform that is regularly repeated at intervals, and E is having no regular pattern but it is perceived as noise. Okay, so complex pattern with a regular repetition will be a pleasant music. So this irregular pattern of complex waves will be called as noise. So again the three important properties of sound waves, that is the amplitude or loudness, frequency or pitch or tone, and then impedance. So this impedance is resistance offered by medium to sound waves. So here the two important properties of sound. One is loudness. So it is the strength of sound. Loudness denotes the appreciation of sound intensity, and it is expressed in decibels. So 0 decibel is determined as or taken as the reference or standard sound. The frequency or pitch or tone of sound determines the number of cycles per second. Pitch or tone denotes the appreciation of frequency of sound waves, and it is expressed in hertz. And if we see about the intensity property of sound, it is defined as the power transmitted by sound wave in a unit area. So this intensity is depend on pressure and velocity average taken over whole cycle. So intensity, the formula for intensity is peak pressure multiplied by peak velocity divided by 2. And the displacement produced by sound waves vary with frequency if the intensity is constant. Low frequency vibrations produce greater displacement. Okay, so if the intensity is constant, so displacement produced by the sound waves vary with frequency. So lower the frequency, vibrations produced are greater. That is inverse proportion. So this intensity depends on the pressure and velocity which average taken over the whole cycle. Sound is a perception of pressure waves generated by vibrating air molecules. So this is you can see in this picture displacement produced by the sound waves. So it depends on the frequency. So the amplitude of sound is nothing but the height of the wave from the zero line, and then the period is the displacement between or the distance between time period between the two waves. So simple harmonic motion is a periodic motion that undulates around a null point with equal amplitudes. Amplitude is the maximum amount of displacement from null point in one direction. So the period of cycle is the inverse of its frequency and represents the duration of a single cycle. Pitch is another important property of sound which will be determined by the frequency. So the pitch discrimination is best in 1000 to 3000 Hz range. Why? Because here amplification of the sound waves is better in this range, and it is poor at high and low pitches. Average individuals distinguish 2000 pitch, so that is pitch discrimination. For musicians, it is very important in pitch discrimination, and this is determined by the cortical plasticity. The pitch of an average male voice in conversation is about 120 Hz, and for average female voice it is about 250 Hz. And the human auditory field. So you can see here that this is a conversation area, that is intensity for that normal conversation is 40 to 60 decibels. Okay, so the human ear is sensitive to sound over wide range of amplitudes ranging from 0.0002 to 200 dynes per centimeter squares. It can detect the difference between two sounds occurring 10 microseconds apart in time. So this is the normal auditory field, which is very wide range. Okay, so the threshold for hearing will be exactly around 40 decibels. So the frequency of normal hearing will be 1000 to 2000 Hertz per second. So up to 20,000 we have the auditory field, and starting from here it will be 20 Hertz to 20,000 Hertz. And ear acts as a transducer for conversion of sound energy to electrical energy. So this picture shows the normal hearing mechanisms from the external ear, which collects the sound, and then middle ear acts as a conductive or transducting mechanism, and inner ear converts the nerve impulses into the electrical impulses and then send the signal to the brain centers. So binaural auditory processing areas. The natural resonant frequency for the external auditory canal is 3000 Hz, and for tympanic membrane it is 800 to 1600 Hz, and for middle ear it is 800 Hz, and the ossicular chain in the inner ear is 500 to 2000 Hz. And the functions of external ear are sound collection and increasing pressure on the tympanic membrane in a frequency sensitive way, and then sound localization. So if we see the parts of the external layer, it is having mainly the pinna, external exposed part, and then the ear canal or auditory canal and eardrum, and a small depression is called concha. So the pinna is a cartilaginous expanded portion covered with skin projecting from the side of the head. So this is the cartilaginous expanded portion, and it helps to collect sound waves and to localize the source of the sound. And then the auditory meatus or outer ear canal, which is 2.5 centimeters long. It runs forwards and inwards medially. Okay, so this is forwards and inwards medially, and then it helps in transporting the sound waves to the middle ear. It is lined with skin which secretes wax. So here there will be secretion of wax from ceruminous glands and oil from sebaceous glands. So which by trapping the foreign bodies keeps the ear canal clear. It terminates at the tympanic membrane or eardrum, which covers the middle ear. Okay, so this is the entire external ear, pinna and then auditory canal. So pinna helps in collecting the sound waves and also localization of sound, and ear canal helps in the trapping of foreign particles with which by which the secreting oil secreting and wax secreting glands, ceruminous glands and sebaceous glands, and also it helps in the transmission of sound waves from external to middle ear. So in this picture we can see the conduction of sound waves by the external source. So there will be compression and rarefaction, compression waves and rarefaction waves. So these sound waves are taken from a small area. There will be divergence and the spreading of sound waves. Again, this will be converged into the very small external auditory canal. So this is the pinna and focused into the external auditory canal. The vibrations pass down the external auditory canal and strike the tympanic membrane. And sound collection. The pinna concha system catches sound over large area and concentrates it to a small area of external auditory matters. This increases the total energy available to the tympanic membrane. Okay, because of spreading out of sound energy by inverse square law, a larger receiver will pick up more energy. These structures amplify the human hearing sensitivity by perhaps a factor of 2 to 3. So larger area is present for receiving the sound waves. So spreading out of sound energy by inverse square law, larger receiver will pick up more energy. So that is again converged into a smaller area of auditory canal. Some features of external canal. It is open on one end only. The impedance of eardrum is about 3 to 4 times more than air. 30% of incident energy gets reflected from external canal, and it is efficient in conducting sound in frequency range of 3 to 5 kHz, and it cuts off unwanted frequency, helping in better speech discrimination. So varied frequencies will be entering into the external canal, but it cuts off unwanted frequency so that speech discrimination will be better. Pressure increased by external auditory canal. If a tube which is closed at one end and open at other is placed in a sound field, then pressure is low at open end and high at close end. So the external ear, that is it is open at one end only. So if we see an example of a tube which is closed at one end and open at other end is placed in a sound field, then pressure is low at open end. So here the pressure will be low and high at closed end. So this phenomenon is seen same in external auditory canal at 3 kHz frequency and at concha 5 kHz frequency. Okay, so at open end the pressure will be low and at closed end it is 5 kHz. The two main resonance are complementary and increases sound pressure in the range of 2 to 7 kHz. So how the external ear helps in sound localization means, because of its shape, the pinna shields the sound from rear end and it changes the timbre or quality and helps to localize sound from in front or back. The cues for sound localization from right or left are: sound waves reaches the ear closer to sound source before it arrives in the farthest ear. Okay, so the ear which is closer to the sound source will be hearing the sound waves first, and then the sound is less intense as it reaches the farthest ear because head acts as a barrier. So the right or left ear, suppose the sound is coming from right ear, so right side, the nearest or closer ear will be right ear. So sound wave first reaches the right ear before arising in the farthest ear, that is the left ear. And as the sound reaches the farthest or the other ear, it will become less intense because head acts as a barrier in between. And these are the two cues for localization of sound. And auditory cortex integrates these cues to determine the location of sound. The total gain or total effect of reflection of sound from head, pinna and external canal resonances is to add 15 to 20 decibels to sound pressure over frequency range of 2 to 7 kHz. So this is the total effect of reflection of sound from head or pinna and external canal. So to add 15 to 20 decibels to sound pressure and over the frequency range of 2 to 7 kHz. So now the conduction of sound waves from tympanic membrane to ear ossicles. So tympanic membrane, it is a part of middle ear. So middle ear is having three parts: tympanic membrane, and then the ossicles, and then the eustachian tube. So tympanic membrane acts as a pressure receiver. It is sensitive to pressure changes in the sound. And then resonator. It acts as a resonator. It vibrates with the pressure changes and it critically dampens the sound ends. And then the ear ossicles. So there are three ear ossicles, incus, malleus and then stapes. So I am not going to explain about all this. So these three ossicles, what do they do means they help to magnify the intensity of sound waves. So we will see in the coming slides how these ossicles help in magnifying the sound waves. And then the eustachian tube. So this tube connects the middle ear cavity with the pharynx. So its pharyngeal opening is closed, but it can be opened by swallowing, chewing or yarning. So it serves to equalize the pressure on two sides of the tympanic membrane when the atmospheric pressure decreases or increases. So this eustachian tube will be helping in equalizing the pressure between the tympanic membrane and the pharynx. So next is the functions of middle ear. It couples sound energy to cochlea and it helps in impedance matching. And the special reflex is present that is called tympanic reflex or attenuation reflex, which is a protective reflex. It physically protects the cochlea and there will be phase differential effects. So that is, it couples sound preferentially to only one window, thus producing differential pressure between the windows required for involvement of or movement of cochlear fluid. So windows means round and oval window which are present in the middle ear. So it couples the sound preferentially only to one window which produces a phase difference, okay, differential pressure between the windows required for the movement of cochlear fluid. So middle ear acts as an impedance transformer. So what is impedance? It is defined as the resistance offered by a medium for transmission of sound. So it is the resistance offered by medium for the transmission of sound. Middle ear acts as an impedance transformer or the mechanism is called impedance matching mechanism. So the cochlear fluids have an impedance equal to that of seawater. So middle ear ossicles are suspended by ligaments. Axis of rotation of ossicles and axis of suspension by ligaments virtually coincides with their center of inertia. At low frequencies, the ligaments play an important role in maintaining ossicular positions by elastic effect. And middle ear converts the low pressure, high displacement vibrations of eardrum into high pressure, low displacement vibrations. This is suitable to drive the cochlear fluids. Okay, so the middle ear converts the low pressure, high displacement vibrations of the eardrum to high pressure, low displacement vibrations, which is suitable to drive or uh, give the movement to the cochlear fluids which are present in the inner ear. Suppose if there was no middle ear system, 99% of sound waves would have reflected back from the oval window. And middle ear, by its impedance matching mechanism, it allows 60% of sound energy to dissipate in the inner ear. Okay, so if there is no impedance matching between the by the middle ear, there will be 99% of reflection of sound waves from the oval window. Because this matching system is present, 60% of sound energy is being dissipated to inner ear. So that is the movement of cochlear fluid is taking place from the oval window because of this impedance matching mechanism. So only 60% of sound energy from tympanic membrane gets transmitted and absorbed in the cochlea. Without middle ear, only 1% of sound energy would have been absorbed by the cochlea. So the middle ear acts as a lower frequency sound dampeners. So middle ear efficiency is best at 1 kHz. There is transmission loss of low frequency sounds due to elastic stiffness of middle ear ligaments. Annular ligament is the most important. Air inside middle ear cavity also dampens low frequency sound transmission. Grommet insertion improves transmission of low frequency sounds. So coming to the impedance matching by the middle ear. The first one is the area of tympanic membrane relative to oval window. So there are three important steps or three important points for the impedance matching. One is area of tympanic membrane relative to oval window, and the other important point is lever action of middle ear ossicles, and then the shape of the tympanic membrane. So this is the first point, which is the area of tympanic membrane relative to oval window. So this is a bigger area and this is very small area. Total effective area of tympanic membrane is 69 mm square, whereas the oval window or the area of stapes footplate is the oval window, which is 3.2 mm square. So 69 and 3.2. So the effective aerial ratio, 14:1. So thus by focusing sound pressure from large area of tympanic membrane to small area of oval window, the effectiveness of energy transfer between the air to fluid of cochlea is increased. Lever action of ear ossicles. So the main point for this lever action is that the handle of malleus is 1.3 times longer than the long process of incus. So this is with the center point or axis of rotation. So taking this as center point as fulcrum, so this there will be some conversion or change taking place, that is low pressure with long lever action at malleus handle to high pressure. So low pressure is converted to high pressure at the long process of incus. Okay, so this will be the center point and this is one side and this is other side. So you can take as seesaw. So one will be low pressure and other will be high pressure. So this will be converted to uh, high pressure at incus long axis process of. And the other important point for impedance matching is shape of the tympanic membrane. So tympanic membrane is this inward shaped. Okay, so it buckles as it moves to and fro. This reduces malleolar movement. So buckling means moving aside, tucking inside, going inside. Okay, so you can see these blue lines. And this thing reduces the malleolar movement. So tympanic membrane thus acts as a mechanical lever. This causes high pressure low displacement system. So the most important factor in the middle ear's impedance matching capability comes from the area ratio between tympanic membrane and stapes footplate or oval window. So total area of tympanic membrane is 90 mm square. So functional area of tympanic membrane is 2/3 area and area of stapes footplate is 3.4 mm square. So effective aerial ratio is 14:1. So thus by focusing sound pressure from large area of tympanic membrane to small area of oval window, the effectiveness of energy transfer between air to fluid of cochlea is increased. Okay, so because of this aerial difference, effective aerial ratio is 14:1. So the sound pressure from large area of tympanic membrane to small area of oval window, the energy transfer is increased. So Eustachian tube equilibrates the air pressure in the middle ear with that of atmospheric pressure, thus permitting tympanic membrane to stay in its most neutral position. A buckling motion of tympanic membrane results in an increased force and decreased velocity to produce a four-fold increase in effectiveness of energy transfer. So this is again the Eustachian tube which is present in the middle ear. It equalizes the pressure between the ear and the atmospheric pressure. That is its opening into the pharynx. A buckling motion of tympanic membrane increases the force and decreases the velocity producing a fourfold increase in effectiveness of energy transfer between the middle ear to inner ear. The combined effects of area ratio and lever ratio gives the middle ear output a 20 decibel gain theoretically. In reality, the middle ear sound pressure gain is only about 20 decibels. This is due to fact that tympanic membrane does not move as a rigid diaphragm. So total transformer ratio is 14 into 1.3, that is 18.2:1. And next, the phase differential effect. Sound waves striking the tympanic membrane do not reach the oval and round window simultaneously. There is a preferential pathway to oval window due to ossicular chain. This acoustic separation of windows is achieved by intact tympanic membrane and a cushion of air around round window. This contributes 4 decibels when tympanic membrane is intact. So the sound waves striking the tympanic membrane do not reach both the windows simultaneously. So preferential pathway to oval window is present because of oscillator chain. So this acoustic separation of windows is achieved by intact tympanic membrane and cushion of air around the round window. So this difference contributes 4 decibels when tympanic membrane is intact. So middle ear muscles. So what is their role? Tensor tympani muscle attaches to the handle of malleus. It pulls the drum medially. And stapedius muscle attaches to the posterior aspect of stapes. Contraction of these muscles increases the stiffness of ossicular chain, thus blunting low frequencies, and it decreases a person's sensitivity to their own speech. Protective functions of middle ear muscles. Stapedius contraction can reduce transmission by up to 30 decibels for frequency less than 1 to 2 kHz, and for higher frequencies this is limited to 10 decibels. Only the stapedius muscle contracts in response to loud noise in humans. The whole stapedial reflex arc has 3 to 4 synapses. The stapedial reflex latency is 6 to 7 milliseconds. So this is the important protective reflex by mid-ear. When loud sounds are transmitted through the ossicular system and from there into the central nervous system, a reflex occurs after a latent period of only 40 to 80 milliseconds to cause contraction of stapedius muscle and tensor tympani. So this tensor tympani muscle pulls the handle of malleus inward while stapedius pulls the stapes outward. These two forces oppose each other and thereby cause entire ossicular system to develop increased rigidity, thus greatly reducing the ossicular conduction of low frequency sounds. So lastly, some middle ear damage scenarios or applied aspects of middle ear. So damaged middle ear can cause loss of impedance matching or transformer mechanism, and differential pressure levels between the two windows could not be maintained properly, and scala vestibuli is more yielding than scala tympani. Differential movement of fluid is still possible. Small compliance of annular ligament in comparison to much larger compliant round window could again cause differential pressure changes. So in today's class, we have seen the principles of acoustics, some important properties of sound, and then we have seen the external ear parts and its functions, and then middle ear parts and their functions. So from today's class, in the exam, for examination purpose, you will be getting short questions. Okay, short and very short also. The important questions are impedance matching and attenuation reflex or tympanic reflex. Okay, so the assignment for today's class is, what is the mechanism of impedance matching? So the 3 points which I have told you in this class, so you write down in a detailed form, make a notes and then send to me, and also the attenuation reflex or the tympanic reflex, which is a protective mechanism. So the ratios, the points which I have told you in impedance matching, if you don't understand it clearly, so read again from the textbook. So how that effective areal ratios came, and the tympanic membrane also, its ratio area is also added lastly, and the effective transformer ratio is 18.2:1. How all those came? So you just read from the textbook on your own and also listen to the class, and then you will be able to understand and make a notes of it and send to me in Telegram. So thank you all.